Today we start chapter 4, which is about solving systems of equations. And there's really two ways that this is typically done. But in the first section, we look at a third way, which is not really a very good way to solve these systems, but it is a really good way to get a picture of what's really happening. So in 4.1, we're going to look at what a system of equations is, and then we'll look at what it looks like graphically, and we'll kind of get an idea of how these things work. And then when we get to 4.2 and 4.3, we'll come up with ways of solving these that are more practical. So first, let's talk about what a system of linear equations actually is. Well, some of it you can see in the words. It's still a linear equation. Like when we solved the first equations we were solving in this class, we had that little handout where you go through the steps and we were solving these linear equations. So the only difference is now it's not a linear equation, it's a system of linear equations. So basically, a system of linear equations is two or more linear equations. So, as an example, let's say we've got this problem right here. We've got this linear equation 3x minus y equals 7. And earlier when we were working with formulas, we would solve an equation like this, for instance, for y. And if we solve this for y, we would have this would be an equation of a line and slope intercept form, if you remember those from the early days of this class. But for the system, we need more than just one equation, so then we have another equation that is associated with this equation. So with a system of equations, we need to find an x and a y that works here and here. The same x here and here and the same y here and here that makes both of these true. So as you can imagine, solving just one equation was super fun. Now we're going to have to solve two of them at the same time. So in other words, our solution will look like this. So I have this solution, and there'll be an x and a y. So we basically have to plug in an x here and a y here. This is one way of stating the solution as a point, because you'll see in this section, if we graph this line, then we graph this line, if there is a solution, it's where these lines cross each other. So you can find solutions that work for just one of them. Like for instance, this first equation, if I let x be 0 and I let y be -7, that would work here, right? Or for this one, I'm just picking easy ones that are easy to see. If I let x be 4 and I let y be 0, this will work. But there's only one point that works for both of these. The only thing that works for both is 2, -1. This is the only pair that works for both of these. So when we have a system of linear equations, it just means two or more linear equations like this. For us, it's always going to be two. In reality, there will be many more. Like in an applied setting, there can be hundreds or thousands of these linear equations, and there can be hundreds or thousands of variables, and we need to find the solution that works for all of them. So just to make it official, let's write down what a solution is. So we can say a solution to a system of linear equations is an ordered pair that is a solution to both equations. So a couple things to notice here. It is an ordered pair, right? Just like this, it's an ordered pair. If you remember when we talked about ordered pairs, it's a pair, meaning there's two numbers, and they're in order. It's x comma y. And so the solution is an ordered pair that is a solution to both equations. Now this ordered pair is for us pair meaning two because we've got two variables. So this is a solution that'll work for us because ours are always going to have just two variables. So if we think about what this is an equation of a line, this is another equation of a line. If you graph two equations of lines, there is really only three things that can happen, only three. And this is important for us to know. I'm going to draw these three situations, and for the rest of chapter 4, if you understand these three situations we're going to talk about, the rest of chapter 4 will make a lot more sense. So I'll say there are solutions to a system of linear equations in two variables. And there are three things that can happen. Now in math they always say in two variables. What in two variables means is with two variables. So for us we're always going to have two variables. And for this right here, this solution, there are only three possibilities. And we'll consider each one of them. So see if I can squeeze them on here. There's a lot more room on I have the whole whiteboard to do this. Let's see if we can make this work. So we basically need three of these. Actually, let me see if I can move this thing a second here. Oh, look at that. Doing some magic here. Look at that. Oh my gosh. Okay, they seem to be getting a little smaller as I copy them. But anyway, we got these three. And these are just XY planes. So I guess I should have done this first. But you got X and Y for all of these. So XY planes. And here's what could happen. We could have a line that comes through like this. We got this line going through here. That's one of the lines. Then we got this other line that maybe goes through like this. So you got these two lines, and in this case they cross at this point right here. So we've got this point where they cross this XY. It's some X coordinate, right? Some X coordinate here, some Y coordinate here. That's typically what happens. This is typically what we actually want to happen. So you've got some X coordinate and some Y coordinate. And what that means is there is one solution. So that was like the example above, where we had the system of equations, and we said there's the one point that's the solution to both of them. So if we were to graph those lines, they would cross like this. So that's one thing that could happen. Another thing that could happen is, let's say we have our one line goes like this, and we make our other line, and it goes like this. It's parallel. So in this case, there's no solution. So there's like this red line here. This represents all the solutions to this equation. Like all these, like this point right here is an XY. There's an XY point. And if you plug in that X coordinate and that Y coordinate of this point, it would solve this equation represented by this red line. Well, the green line is up here, and they don't have any points in common. So here's all the solutions to the equation that is graphed as a red line. Here's all the solution to the green line, and they never touch. So there's no solution. So that's the other thing that could happen. And there's only one more thing that could happen. Only one more thing. It could be that you graph the red line and it goes like this. And then you graph the green line and it goes like this. It's the same exact line. They're the same. And in that case, every point that's a solution for the red line is also a solution for the green line. So in here, this is when we have infinitely many solutions. So for every single problem that we do in chapter 4, every single one of them, where we've got a system of equations and two variables, we're going to get one of these three. That's it. It's going to always be one of these three. And that's true for a system of linear equations and any number of variables. You can only get one solution, no solution, or infinitely many solutions. So geometrically, what's happening when you have one solution, you can see by the picture we have intersecting lines. All right, so we want to understand the geometry of this situation too. When you have one solution, it means that if you were to graph those equations of each of those functions, each of those linear equations, you get intersecting lines. When there's no solution, it means we have parallel lines. And when there's infinitely many solutions, it means it's the same line, which is called coincident lines. Just write this. It means it's the same. Coincident lines mean they're the same lines. So another thing to notice, geometrically, for sure if these intersect, they for sure have different slopes, right? The slope of this red line is definitely different from the slope of this line. So it's another thing to make note of. They have different slopes. And sometimes that could be important to notice that. So I'm going to just say, when you see the equation of a line, if they have different slopes, you know immediately what situation you're in. There's going to be one solution. Because you can see in these other cases, these have the same slopes. Now what's different here though, if you look at this, remember this is a y-axis, so that point right there is the y-intercept. That's the y-intercept. So these lines have different y-intercepts. So while the slopes are exactly the same, the y-intercepts are different. So we can make a note of that. So different y-intercepts. Different y-intercepts. And put this in red. Okay, then when you have this coincident lines, which are the same lines, everything's the same slope, same y-intercept. So these have the same slope. Same y-intercepts. And this picture, like I said, if you understand this picture, everything we do in chapter 4 will make a lot more sense because every problem we're working on can be interpreted geometrically as one of these three. So there's some other wording that the book uses sometimes, and a lot of it is because it will be used later in higher math classes. So I'm going to mention these words, although I'm not really going to ask you about it. But when you have a solution, there's just one solution. Basically, if you have any number of solutions, as long as there is a solution or infinitely many, this is where the book will say the system is consistent. So this one is also the same situation. System is consistent. So if you see the book use this word consistent, it just means there is a solution. Right here there's one solution. Here there's also a solution because there's infinitely many. Every single point on both of these lines is a solution to the system of equations because the lines are the same. So System is consistent means there's a solution. So in this case, we would say the system is inconsistent. Okay, that just means there's no solution. So there are solutions to this first case and the third case. There's no solution here. So this is the wording that you'll see in the book. Occasionally. It's not going to be a big part of the class. Like I said, it'll be used in higher math, so some of you will see this later, especially if you have to take linear algebra, or sometimes in applied business classes you'll see it in business math, because systems of equations are studied in business math also. Then another term that you'll see sometimes is independent. So this is another one the book will mention occasionally. I'm not really going to say much about this as far as asking you questions about it, but in this case we can say the system is independent. Okay, now when you see this word independent, it just means the lines are different. These are different lines. The lines are not the same. So there's another case where the lines are not the same. That's this case, right? These lines are not the same. So this system is also independent. System is independent because these lines are different. Now these lines are the same. So this system would be said to be dependent. Dependent. Which just means the lines are the same. Now of all of this stuff, what's the most important is knowing this first part here. There's one solution. In this case, the lines intersect if you were to graph them, and they have different slopes. Different slopes makes it easy to see, because see how these are the same slopes, same slopes? You can know immediately, if you have two equations of lines and they're in slope-intercept form, you see the slopes are different, for sure you're going to have one solution. If the slopes are the same, you're in one of these two cases. These are like the oddball cases, which you'll see. The vast majority of the cases that we see are this first one right here, because that's where we're going to get one solution, which is usually what we're looking for. These are kind of the oddball cases. Okay, so this is pretty much what 4.1 is about. So let's take a look at the homework problems, and I may refer back to this picture of these three situations from time to time. So first one I want to take a look at is number 4. So number 4 says, it gives us a system of equations, and it asks if a particular point is the solution to the system. So number 4 says x minus y equals 3, and x plus y equals 5. And it gives us this point 4,1. So here's the question. It says, determine if the given point is a solution to the system. Okay, here's our system of equations. Why do we call it a system of equations? Because there's more than one. Right, there's more than one, and they're linked. We're looking for an x and a y that works for both of these systems, right? Or works for both of these equations. So a system of equations just means there's more than one, and we need to solve both of them. So to see if this works, all we have to do is we take this point, and remember this is x, this is y. It's an ordered pair. They're in order. So to see if it works, I take this 4 and plug it in for this x. Take this 1 and plug it in for y. And then we just check. So to check, I'm going to check this first one. X minus y equals 3. 4 minus 1 equals 3. Right? I'm just checking this one. And that checks. So that's good. But remember, for this to be a solution to the system, it has to work in both of these. So you just check. Plug in 4 for x and 1 for y. It works here. So now let's try this one. We do the same thing here. Come around here. And I'm going to plug in 4 for x, 1 for y. And if we do that, we will get 4 plus 1 equals 5. And that checks also. So the answer is yes. The answer is yes, because what we're saying is this pair, this ordered pair, is a solution to this system. It's a solution to this system. So that's how we answer that question. Now I know what you guys are probably thinking. Come on, Kurt. Give me something a little more challenging, maybe some fractions. It's like I can read your mind through the ether. So let's try this one. Let's try number 6. Number 6 has some fractions. So number 6, same question, but here's our equation this time. Y equals negative 1/3 x plus 2, and x equals 2y plus 6. 2y plus 6. And the point that they give us this time is the point 9, negative 1. So it's basically the same thing. So try it out on your own and then come back. That's the best way to do this. So go ahead and give it a try. And okay, hopefully you gave it a try. Who didn't? Come on, you got to give it a try. Don't just watch me do it. Okay, so basically what we have to do is plug in this for x, right? Plug in this for y. We do that to each equation. So just looking at the first one, if I do that, I'm going to get negative 1 equals negative 1/3 times 9 plus 2. Okay, negative 1/3 times 9 is like this, right? Times 9 over 1. Remember, when you multiply fractions, you go straight across. And you could cancel first two if you want to. But if you didn't, you'd get negative 9 over 3, which is negative 9 divided by 3, which is going to be negative 3. So coming back down here, we get negative 1 equals negative 3 plus 2. Negative 1 equals negative 1. So it works for the first one. Now we still have to check for the second one, right? So we still have to check that second one. So we come back in here, get rid of this. We know that it works for the first equation. Now what we have to do is try it for the second equation. So I'm going to plug in 9 for x and plug in negative 1 for y and see if that one works. So let's make a little space here. So to try it out, we would get, let's see, 9 equals 2 times y, which is negative 1 plus 6. 9 equals negative 2 plus 6. And we can see that's not going to work. So as soon as you get here, we have a frowny face because we're so sad. We were hoping it was a solution, but it's not. So to answer number 6, determine if the given point is a point to the solution, we just say no, it's not. This ordered pair is not a solution to this system of equations because it only solves one of them. To be a solution to a system, it needs to solve all the equations in the system. Now for us, we're always going to have 2 equations, but number 6 does not work. So that's how you do those. You just have to plug them in to both of them and see if they work. Now, I had mentioned at the beginning that there's really 2 ways that are typically used to solve equations, and then there's a third way. The third way is solving by graphing, which is not a very good way, but it is really good to just understand the geometric interpretation of what we're doing. So we're going to do one of those right now. So we'll try number 32. And there's a grid in your book. So this one's way easier to do in the book because you have a nice grid of the XY plane. And so it's kind of easy to see what you're doing. But on the whiteboard, I just typically make a grid. So I'll do that. I'm going to make a grid and then try to solve these by graphing. So here is the grid. Go 1, 2, 3, 4, 5, make a few of these. And as soon as you start doing this, you're going to see why this is not a great method, because you have to like eyeball the solution from your grid. So they're going to make these cross in nice points so that it'll be at least doable. But if you have fractions or anything for solutions, it's really, really tough to do this way by hand. So just looking at these, well, look at this. This is a line we've seen before. Is this a horizontal line or a vertical line? We've seen this one before. Just remember, it says x is 3 no matter what. No matter what y is, x is locked in at 3. So if we graph that line, it is going to be right here. It's like no matter what's happening with y, x is always 3. So it's a vertical line. So that is the line x equals 3. So then we have to graph this line. So to graph this line, we could, use what we did before. Earlier in the year, we graphed these systems, or we graphed these equations of lines. And there's really a couple of ways we did this. One way is we solved for y and put in slope-intercept form. The other way is we found the x-intercept and the y-intercept. So a lot of times that's the easiest way. So if you remember what we did earlier is we would take a little t-table like this and we'd say, I'm going to see what happens when x is 0 and then see what happens when y is 0. So when we come up here, we let x be 0 and see what y is. So if x is 0, so to find, oh, that's not what I wanted. Okay. To find this one, we let x be 0. So if we do that, we would get 4 times 0 plus 3y equals 9. When x is 0, we're going to find the y-intercept, remember. So 4 times 0 is 0, so 3y equals 9. So you divide by 3, and you get y equals 3. So that means this is the point 0, 3. So I'll put the point 0, 3 on here. So x is 0, y is 3, so that's right here. Right, this is the point 0, 3. Now I need to find this one. So for this one, we let y be 0. So if I let y be 0, do this over here. So I'm going to let this y be 0. So we will get 4x plus 3 times 0 equals 9. 4x equals 9. So then we have to divide each side by 4, and we get x equals 9/4. So 4 goes into 9 twice with 1 left, so it's like 2 1/4, or 2.25. So we have, let's see, 9/4, which gives us this point. Here's where it gets a little hard to do this very well by hand with graphing, because we have 9/4, it's like 2.25. So when x is 2.25, it should put us about right here, right? When x is 2.25, y is 0. So here's that point. And then to make the equation of a line, we draw a line connecting those 2 points. And then we just have to kind of eyeball it, and hopefully it will work out okay, where we can tell what the solution is. And the solution is this point right here. So we are in the first situation. There's only one solution to this equation. Let me just draw this line a little bit better. Right, these lines, because they're straight lines, they're only going to cross once. So this is the line 4x plus 3y equals 9. They cross at that one point, and then we have to guess the solution. So looking at that point, it looks kind of like it looks like 3, -1. And that is what the answer is. So you can see that it's a little tricky graphing these, which is why we only do this in 4.1. In 4.2 and 4.3, we're going to find much better ways to do this. But this is how we have to do it now. We graph the equations of lines, we kind of eyeball the solution. And again, in your book, you'll have a better grid, so it is a little easier to see than when I make it by hand like this. But in this section, here's how we find the answer. We graph this, and we see if they cross. There's only 3 things that could happen. They cross in one point, or they could be parallel where they don't cross and there's no solution, or they could be the case where I draw the first line and I draw the second line, it's the same line. In that case, there's infinitely many solutions. So I want to show you one of the kind of oddball cases, which means either they're parallel or they're the same line. So let's look at one more just so you can see how this looks. Let's try number 36. So 36 says x plus 3y equals 0, and minus 2x minus 6y equals 0. Now this one, we could graph them both, by putting them in slope-intercept form or finding the x-intercept and the y-intercept. And so we can do that. Also, if you put them both in slope-intercept form, you're going to see that they're the same line. So then you wouldn't really even need to graph them. But let's just say we're not sure what's happening. We're just going to graph both of these. So I make a quick little grid here. X and Y. All right, so looking at this first one, I'm going to do the same thing, make a little t-table. And I'm going to plug in 0 here, 0 here. So if I plug in 0 for x, I get 3y equals 0. So if I plug in 0 for x, I get 0. Whoops, I get 0 plus 3y equals 0, which means 3y equals 0, which means y equals 0. So as soon as you get 0 here, that means I'm going to get the same thing if I plug in 0 for y. It means this line's going through the origin. Right, so if I plug in 0 for y, I get x equals 0, which means I need to pick a different point. So let's pick a different point here. And base, I'm just going to pick an easy point. I'm just going to let x be... I'm going to let x be 3, because then this will work out nicely. But you can really let x be anything at all. So if I let x be 3, I get 3 plus 3y equals 0. Subtract 3 from each side. 3y equals -3. So then if you divide by 3, you get y equals -1. So then this is a -1. So this gives me the point 0, 0 and the point 3, -1. So I can plot those points and then make this line. So it goes through 0, 0. And when x is 3, 1, 2, 3, y is -1. So it's going through there. So I'm just going to make a picture of that line, and it goes like this. So that's the first line. So now I need to make the second line. So I'll do the same thing here. Maybe this one I'll do up here. Make a t-table. And this one's going to be similar. If I plug a 0 in for x, 0 in here, I'm going to get, if I plug a 0 in here, that's basically gone. Get -6y equals 0. The only way that can work is if y equals 0. So I get the same thing. So this one is also going through the origin. And then just to pick another point, it doesn't really matter. And let's pick, let's go with a 6. And again, this just because any number works, but I chose this 3 purposely because I didn't want to get a fraction. Same reason I'm choosing this 6. Really, anything works, but I'm just picking these to make it easier to not have to eyeball a fraction on here. If you pick a 1 here, you'll get a fraction, and it's okay in the book because you have a grid, but it's a little tougher here. So that's why I'm purposely picking a 6. So in other words, if I plug in this 6, we're working with this equation. Now if I plug in 6 for x and solve for y, here's what we would get. If I plug in a 6 for x, I'll do this over here where there's some room. You get negative 2 times 6 minus 6y equals 0. This is negative 12 minus 6y equals 0. And what we would do to solve this is we would add 12 to both sides. And then we would get negative 6y equals 12. So then we would divide by a negative 6. That cancels, and we get y equals negative 2. So you get negative 2, so this is a point 6, negative 2. So now I'm going to plot this one using a different color. So we'll get 0, 0, so it's going through the origin. And then we get 6, negative 2, so we get 1, 2, 3, 4, 5, 6. Negative 2, 1, 2. And look at that. When I connect this, I'm on the same line. So those are the same line. So to answer number 36, the answer is infinitely many solutions. Here's the answer. Infinitely many solutions. And that is all the answer you need. That's all I would be looking for. The book's going to say, well, that means that they are dependent equations. Geometrically, it's because they are the same line, or the book will say coincident lines. We just have to know that. If you remember what an equation of a line is, just a quick review. So when we were looking at this first line here, and we made this grid system, and we plotted the blue line here, we plotted only 2 points, 0, 0, and 3, negative 1. But I could plug in any number we want for x, and there would be a corresponding value for y. And if we did that, we would get every single point on the graph here. This is just like a geometric picture of this t-table if we put in infinitely many points. Right, so every point on that blue line is a solution to this equation. And every point on the green line is a solution to this equation. So the solution to the system of equations is all these points on the line. So there's infinitely many solutions. It doesn't mean everything's a solution. This point right here, 2, 1, that's not a solution, right? All these points out anywhere that's not on the line is not a solution. So there's infinitely points that are not solutions also. But we just have to say there are infinitely many solutions because these, that's all we need to say right here, but it's because these are the same line. So try 4.1. It's a little tedious because of all the graphing, but things will get better in 4.2 and 4.3. We'll come up with a better system, and it's more important also. So 4.2 and 4.3 are the methods for solving systems are more important than this geometric method that we're using. But the geometric method is good because it shows us what's really happening. So give 4.1 a try, and if you have any questions, let me know.